Okay, this is going to be the second lecture for our chapter 6 on the thermochemistry. And so we're going to start us off with just a little bit of review. Let's go ahead and look at a calorimetry problem. And so in this calorimetry problem, we have a block of gold. So we have 97 gram sample of gold at 785 degrees Celsius. We're going to drop it into 323 grams of water, which has an initial temperature of 15 degrees Celsius. If gold has a specific heat capacity of 0.129 joules per gram degree Celsius, what is the final temperature of the mixture? And it's telling us to assume that the gold experiences no change in the state of matter. So it's still a block of gold all the way through. Now, sometimes when I see this, I do like to draw out what's going on. So I have my block of gold going on there. I have its mass. I know its initial temperature. I can have my water. I know its initial temperature and I know its mass. So maybe I should actually add in an I here just to help us know that it's our mass or our initial temperature. So Ti, right, our initial. And so what we want to remember is that everything that's lost, all the heat lost by the gold, is going to be equal to all the heat gained by the water. And so we have Q, which is our heat, which is MCAT. So that means that our heat capacity of our gold times its mass times its change in its temperature should be equal to the negative of the heat capacity of our water times its mass times its change in temperature. So we can plug in our values there. Now remember that our change in temperature should always be TF minus TI. And our temperature is fine if we leave it in degrees Celsius. We can also convert them to Kelvin. Either one is fine. We just want to make sure that they match. And that's because that change in 1 degree Celsius is equal to the change in 1 Kelvin, which is why it doesn't really matter whether we change them or not, but we just want to make sure that they're both either in degrees Celsius or both in Kelvin. We should then multiply those together. We can pull all of our TFs to one side, which is kind of what we're doing here. And so we get a final temperature of 22.1 degrees Celsius. So the important part is just getting our information lined up correctly and then setting up our equation. From there, it's just some math as we're working our way through. Let's try another one. This time we have a 59 grams of water at 13 degrees Celsius, and we're mixing it with 87 grams of water that started off at 72 degrees Celsius. And we want to find that final temperature. Right? So we start off at 13 degrees. We start at 72 degrees. So go ahead and take a moment, work through your equation, and then you guys can check back in. So moving forward, we got our loss of heat is equal to our gain of heat. And so this is going to be from our hot water over on this side, and this is going to be from our cool water over on this side. Both of them have the same degree Celsius, or sorry, the same specific heat capacity, 4.184, because they're the same material. And so we work our way through, and we can get our final temperature at 48.2. Looking back, I realized that I had those, I had told you the wrong side. This was actually our warm water on the right, and then the one on the left was actually our cool water, and it was the one gaining the heat. But as you can see, it doesn't matter which side you put the negative sign on, as long as you get it in there on one of them, then the math will work itself out. Very good. Now, the reason why we are interested in this is that we want to quantify that heat energy, right? So we want to start to be able to identify how much heat is being transferred by different processes. And so it's not always us just putting a material inside and finding specific heat capacities or things like that. It's really this idea that those two objects are sharing that heat, that this thermal energy is being transferred from one to the other. Because what we're more interested in, right, while in both of these cases that we've shown you so far have been us looking at objects, we're really interested in measuring that change in that heat for a process. And so what we're trying to do is we're trying to measure our enthalpy. And so if we use the same technique, calorimetry, but we do it at constant pressure, what we can see is that our enthalpy and our heat are going to be equal to each other, because our enthalpy is our heat times our pressure and our volume, but our pressure and our pressure is constant. And so then we don't have to worry about the second term. And so all of that energy instead is being released as that heat in that change. So what we can do is we can do our reaction inside of that calorimeter, and we can measure the heat that's being released by it or gained by the water by measuring its temperature change. Now, when we talk about chemical reactions, we're going to introduce a couple of new terms to it. And one of them is going to be endothermic, and one of them is going to be exothermic. So endothermic and exothermic reactions have to deal with the heat that gets released from a chemical process as it's going through its change from reactants to products. So chemical heat, such as like the hot hands and things like that, those are exothermic reactions. What happens is that as that iron inside of those hand warmers starts to change into iron oxide, it releases the heat, and that's how it's warming up your hands. So they feel warm because they're releasing heat, whereas chemical cold packs, they can be like those instant cool ice packs that you might have in a first aid kit. Those are what we call endothermic processes. And so the reason why your hands feel cold is that that endothermic process is pulling in heat, and so it's pulling in from the surroundings, and so that's you. So when you think about it, a hot hand, even though it feels warm, is actually it losing heat. It's losing heat and giving it to you, which is why your hands are feeling warmer. So your hands in this case, that's a terrible hand. That's not that much better. But your hand in this case is going to be your surroundings compared to the system, which is the actual warmer. So hot hands are going to be exothermic. Ice packs are going to be endothermic because of pulling in that heat from the surroundings, which is still your hand. So when we're looking at a reaction and we notice that the flask is getting colder, what is the sign for it? Now that delta H for our flask is going to be positive. And so it's getting colder because it is pulling in that energy. And so the surroundings have to sacrifice that energy in order to make that process go forward. So it's going to be a positive delta H change. And so the idea behind it is that for an exothermic reaction, the surrounding temperature rises due to the release of that thermal energy. And so that extra thermal energy comes from the conversion of some of the chemical potential energy inside the reactants into the kinetic energy of heat as it transitions. And so this happens because during the course of the reaction, bonds between our reactants are broken and new bonds are made in the products. And so the energy that was stored in those bonds that we broke wasn't equal to the new bonds that we made. In fact, there was a decrease in the energy being stored. And so that decrease in that potential energy means that the difference has to be released as heat. And so that's how we make energy with a chemical reaction, is that that energy was actually stored in those bonds. And so now we have to release that heat because we make new bonds and they don't have quite as much energy stored inside. For an endothermic process, that means that the surrounding temperature drops because it's absorption of some of this thermal energy by the reaction. So that means that the reaction's absorbing in some of that thermal energy from the surroundings, and so your surroundings has to drop in terms of its temperature. And this is because the existing bonds that are broken and the new bonds that are made, they also don't line up. Instead, though, of the reactants having more energy in the bonds that we broke versus the bonds that we formed, in this case, our bonds formed have more energy than the bonds broken. So our products have more kinetic energy, or sorry, more chemical potential energy than our reactants, which is why it's taking in energy to drive that process forward. So some of the thermal energy of the surroundings get converted into the chemical potential energy inside of our products. So this is a visual of this. So on the left-hand side, we can see that our reactants had more energy than our products. And so this change is an exothermic process. You can imagine that it's going downhill. So it has to release some of that energy in order to flow that way. So this is when our enthalpy is going to be negative. On the right-hand side, the delta E is going to be a positive. Sorry, our enthalpy is going to be positive, and this is because our reactants have lower energy than our products. So in order for us to go uphill, they have to absorb that energy. And so these chemical reaction diagrams are ways for us to help visualize what's going on inside of our process. We can look at this as being our reactants and our products, and we can look at all the different stages along that reaction as well. So always remember, pay attention to how our energy is being discussed. And then down here at the bottom, we're kind of doing our reactants versus our product side. And so we are going to be primarily talking about enthalpy. And the reason why we want to use enthalpy is a state function. And so as long as we keep our at constant pressure, then it's really related to our heat. And so we want it to be a state function because there's a lot more things we can do with it. If we had just discussed it as heat, and let's say it wasn't at constant pressure, then it wouldn't always be a state function. Our heat changes based on what pathway we take. Whether we cool it a little bit and then heat it a lot and then cool it some more, that amount of heat change does change. But the enthalpy will be the same because the enthalpy is looking at that energy. And so that's just one reason why we need to talk about enthalpy as opposed to just heat. They're not perfectly interchangeable, but they do mean the same thing as long as it's at constant pressure. And so the first thing that we're going to do is we're going to do something that's called writing a formation reaction. And so this is how it's a standard way for us to write about how products are formed. And so what we want to do for a formation reaction is that all of our material that we're making, they start off in their elemental form. So in this case, if we're going to write the formation reaction for carbon monoxide, we're going to start off with carbon in its elemental form and oxygen in its elemental form. Now, what that means is that carbon in its standard state is going to be solid. I'm going to say that she shows up as graphite. And then oxygen in its standard state is going to be O2, and it's going to be as a gas. And so how you know what the standard state is you want to think about how that element shows up by itself. So our metals generally are going to show up as solids except for mercury. Our gases show up as these diatomic molecules except for the noble gases. And so that's how we can line up how we would find that element by itself. And then from there, what we want to do is we want to make 1 mole of the product that we're looking for, carbon monoxide. Now, in order to get this to work, we do have to balance this equation. But the restriction is instead of normally how we would balance it, where we would change all of the values and we wouldn't use any fractions or decimals in our coefficients, the restriction this time, though, is that the product compound has to be a 1. So that means that in front of this carbon monoxide has to be a 1. And so now we can use whatever coefficient that we need in order to keep that true. And so that's why in this example, we can use the 1/2, right? Because we only need 1 of those oxygen atoms. And so we're going to have half of an O2 molecule. And so this is a formation equation for carbon monoxide. So we have our elements starting out. And we're moving those over. So we're going to try another one. In this case, what we're going to do is we're going to look at the formation of, let's see, NH3. Now, NH3 is also a gas. Actually, NH3 is going to be a liquid. Come on. For some reason, my eraser doesn't want to work. Let's try this again. So NH3 as a liquid. So we have to break it down to what elements. So NH3 as a liquid. There we go. And so now we have to break it down to what elements NH3 is made from. So we have nitrogen and we have hydrogen. And how do we normally find those in the elemental state? Well, nitrogen shows up as a gas and it shows up as a diatomic gas. And hydrogen also shows up as a diatomic gas. Yeah, both of them, the nonmetals, both of them, one of those seven diatomic. So now if we want to balance this, well, we only need one nitrogen. So that means that this has to become 1/2. And that's because our product has to be 1 NH3. We can't have it normally as we would balance it where it becomes 2. Now for our hydrogen, we need 3 of them. So we need 1.5 of these. And so we can do it as 3/2. We can also do it as 1 1/2, either one. And so this is going to be our formation reaction. And so you want to be practicing with these. In our worksheet that's linked to today's lecture, then there's going to be more of a chance to continue writing formation reactions and what you can use them for, right? And so I just wanted to make sure that you guys got to see a second one. Now, the reason why we care about that is that we can use these formation reactions to write an enthalpy reaction for that whole process. So remember that our enthalpy change is a... And so we can create that set of reactions, or sorry, we can define the enthalpy of that reaction as by looking at the energy change that happens through that process. Now, because enthalpy is a state function, what we can do is we can break that apart and look at it from all of the energy of all of the products minus the amount of energy for all of the reactants in terms of enthalpy. And that change is going to give us that change in that enthalpy process. So this is a really powerful piece because that means that if we have the formation reactions, so what we were just writing for the different ones, right? So like these, if we can write that out for all of our products and all of our reactants, the energy required to make them, that enthalpy required to make them, the change in them will be equal to the change of our reaction. So it's a really powerful way for us to predict our enthalpy for a different reaction that we might not know or might not have done, as long as we have the standard formation reactions instead. So if we know what they were to make it. Now, one part about this is that these formation equations, these delta HFs, if it's for something in its elemental state, they're always going to be equal to 0. That's because when we found that element, there was no energy or no enthalpy that needed to be put into it in order to kind of produce it. And so they start that out as the 0. That's our neutral state for that element. And then from there, it can be either a positive change if it required energy to make that next product, or a negative change if it required energy to change it into a different state. So that's kind of how they all start. Now, for these delta H's, what it's tied into is this concept called Hess's law. And so the idea with Hess's law is because enthalpy change is a state function, or because enthalpy is a state function, then the change in enthalpy for a stepwise process is the sum of all of the enthalpy changes of the steps. What that means is that if you can take a reaction and you can express it in a series of steps, then that change in that enthalpy for the whole reaction is the sum of each of those individual steps put together. So let's take an example. On this change here, what we're really looking for is this blue, or this purple arrow. We would like to know what it looks like to go from part 1 to part 3 directly. But we don't have the enthalpy change to go from 1 to 3. Instead, what we have is we have the change to go to 1 to 2, and then from 2 to 3. Now, because enthalpy is a state function, what this tells us is that if we want to find this difference from 1 to 3, all we need to do is look at this change of 1 to 2, add that to the change of 2 to 3, and then we can go all the way from 1 to 3. And so that's what Hess's law is describing, is that if we can take that reaction, if we can break it down into smaller steps, those enthalpies changes for all of those small steps will be equal to the overall enthalpy change of that reaction. And so we can do this in a bigger scale, and that's what's going on here, is that this is looking to calculate the delta H for this process. So one way to do this is to go ahead and break it down into all of their different elements. So that's what they're doing in step 1 here, is they're going to decompose it into all of their different elements. Once they've done that, there we go. We can break each one down into its different elements. So our C3H8 is going into its carbon and its hydrogen. Our oxygen's already there as an element. So we have all our reactants broken down into our elements. Then we can look at, well, how much enthalpy does it take for us to form that CO2? So we can take our carbon and the oxygen to form our CO2. And that's what's going on in step 2. Step 3, well, we still have water that we need to form. So we need to form that water. So we're taking that hydrogen and that oxygen to form water. And you can see now we've managed to change all of our reactants to all of our products. And so overall, it kind of looked like this. We had step 1 where we broke apart our C3H8 into its elements. We had step 2 where we took those new elements and turned them into our product. We had step 3 where we then made our water. And so the sum of all of these equations, right, our C3H8 is on that side, our 3 carbons, our 4 hydrogens, our 5 oxygens all get added up. And so you can see how this works out. Our overall reaction looks exactly like the one that we were looking for up here. And so when we're ready to, we can use our enthalpy to find we can use the enthalpy of each of those processes to find the enthalpy change for that entire process. We just have to remember that we need to scale those based on how many moles of each that we make. So as an example, for us to do that conversion of our C3H8 to our carbon and a hydrogen, then we have to find out, So this is like our reaction number one. No, that's not it. So this is like our reaction number one over here, is that we had one, and this was the energy required to make all of that happen. And you can kind of see that that still lines up with the energy of our process there. On our product sides, then those are coming in front. And so we needed 3, and then this is going to be our CO2. And then we needed 4, and so this is going to be the energy required for our H2O. So this was just another way of rewriting these. The difference here is that this delta H, we would just be able to write that as 103.85 because that was a positive change. This one would be a negative 1181. And this one would be a negative 1143 kilojoules because we're dropping down. On the other side, when we're writing these as in this setup, what we're doing is we're basically taking those formation reactions, what we could find from a table, and we're trying to set them up. Now, what we'll notice is in order to get all those signs correctly, we're always going to be doing the products minus the reactants. And the reason why is that if our products have less energy than our reactants, then we should have released energy. And so we should be negative for our delta H. If our products had more energy than our reactants, then we should be a positive for our delta H. And so that's kind of how they're trying to get this set up correctly, which is why both of this sides are products and both of this sides are reactants. And you can see that for our oxygen, that standard enthalpy is 0 because it's in its elemental form. Now, you don't have to memorize the standard enthalpies for all of the different materials. The only thing that you have to know is you have to know that if it's an element in its elemental form, that it's 0. And then the other one would be if I provided you those standard enthalpies, you would know what to do with them. Now, for your homework, you might have to look them up inside your book. They're in your appendix. They're also, some of them are listed throughout the chapter. As you're solving those problems before a quiz or an exam, it would be something I would provide you with. So let's look at another one. So this is our CH4 and our oxygen going to carbon dioxide and water. So we have similar steps. We have the decomposition of the methane. We have the formation of the CO2, the formation of the water again. Now, to get these equations to look correct, we have to make some adjustments. Because if I just added them up as they look like, we would have CH4 as a product, we would have CO2, we'd have H2O, and then on this side, we'd have all of our carbons. And so that doesn't look like the reaction that we need. Instead, what we have to do is we have to flip our top reaction. So that way, instead of making CH4, we're going to break down the CH4. And then, instead of having only one of these water molecules, we need 2 of them. So, for enthalpies, as we work through our Hess's law, the nice part about them is that your delta H will do whatever you do to your reaction. So if you flip your reaction, so that means that you take your products and you make them reactants to your products, then you need to flip your delta H. If you scale your reaction, so if you let's say multiply it by 3, then your delta H would be the same thing, but be 3 times it. So when we try to get our equation set up, we had to flip our first one so that negative delta H became a positive, right? It was a negative here, positive there. We didn't have to do anything to our second equation, so that part was fine. But our third equation, we needed to multiply it all by 2 because we needed 2 waters. So it's the same as this one, but multiply by 2. Now, once we have them all lined up correctly, we just need to go ahead and add them together. And now we have that delta H for that whole reaction. So that's one way to go through and to do it, is you actually write out the equations, you use them to move around. And so this is Hess's law, but with a series of reactions. So this is really good if we know different parts of a reaction, but we might not know the exact reaction that we're looking for. The other way to do it is to use just our standard enthalpies. And so this is that one where we have the sum of all of the enthalpies for our products minus the sum of all of the enthalpies for our reactants. And so then we plug them in. And so a lot of what we'll go through is it all depends on which way you're provided the information. Just remember that, let's say for this one up on top, we have the enthalpy for our product. So this is going to be our carbon dioxide. This is going to be our water. So we have to scale that for two of them. Then we're going to subtract the enthalpy change for our methane and our two oxygens. So depending on what information you're provided with will kind of dictate which way you need to go. Are you given a table with a lot of enthalpies? Then that's how you can find this one, or enthalpies of formation. If you're given a lot of equations looking like this, then you might have to go through this process. So let's look at an example. Use Hess's law to determine the enthalpy for the following target reaction. And so this is our target. So we want to try to get these equations to look the same. So what I always recommend is look for something that's unique to only one of the equations. So our NaCl, right? You see how it's only in option number 2. So this is equation 1, this is equation 2. And so what we want is we want to go ahead and we want to flip this one. And the reason why we want to flip it is that NaCl, we need that to be a reactant. So we can go ahead and flip it. That becomes NO is a gas going to NO plus 1/2 CO2. And that delta H is going to be a positive 38.6. Okay, so that's part of it. Our next one is, well, you can see that that equation by itself isn't going to get our products to line up correctly. So the other part that we need to do is we need to get rid of that NO on the product side. What that means is that we want this to cancel out with this one here. So if we flip this one as well, then our equation looks something like this. Now, what this tells us is that when we add these together, we would get NaCl plus NO going to NO plus 1/2 N2 plus 1/2 O2 plus 1/2 Cl2. And we can start to cancel out things that show up on both sides. So our NO and our NO, we can take those out because it's a product and reactant. And so we can simplify that down. Now that doesn't quite look like what we wanted. And so there's something else that we needed to do first. And that's that we want to scale them by 2. Because it's not enough that we just have one NaCl, we want 2 of them. So we should multiply this one by 2. So that way this becomes 2NO, 2NO, 1 CO2. And then we also need to multiply this by 2. So that becomes 2NO, an O2, and an N2. So as you're working with the equations, your goal is to manipulate them. So that way you can make this one down here, your target equation, identically. So with the flip and multiplying it by 2, we have 2NO plus CO2. This becomes 2NO O2 plus N2. We can take out our NOs, so 2NOCl, CO2 plus O2 plus N2. So that looks like what we're looking for. And so we just want to remember this equation here, equation number 2. We flipped it and we multiply it by 2, so it shouldn't be negative 38.6. Instead, it should be a positive 38.6 times 2. So that's going to be 77 kilojoules. And then on the other side, this one down at the bottom, instead of being 90.3, it should be negative 90.3 times 2. So negative 180.6. And then since we just added those together, we just need to add these together. So we get a total of negative 103.4 kilojoules. And so that's kind of how you set those type of equations up. So you can flip them, you can move them around. Just remember that anything that you do to the equation itself, you have to do to the enthalpy as well. Now, a third way for you to talk about your enthalpy has to deal with the actual bonds, whether they're being broken or put together. Now, this is probably one of your most useful techniques in the sense that you can do it for any type of product or any type of reaction, but it's also maybe the one that differs the most from our practical situation because it's assuming that that bond energy is the same for a particular bond in a gaseous substance, which isn't always the same. The energies associated with all of our different chemicals, a carbon to a hydrogen bond isn't the same energy in all molecules of that carbon to the hydrogen, because it really depends on those other things connected to that carbon as well. So this one is like good and that's very useful, but also it's more of an approximation than the final answer. So for bond enthalpies, what you would do is you would get a table that looks like this. And what this is telling us is this is telling us the energy that's required to break the bond. So they're always given as positive values, and that's because that's how much energy we have to put in to break it. That's also the amount of energy that you'll get back when you form that bond, or energy that you get released when you form that bond. And so when we look at that delta H, it feels a little bit backwards. And that's because the delta H is always going to be the bonds broken minus the bonds formed. And that's because your bonds that you're forming release energy. The bonds that you're breaking require energy. So it always requires energy for you to separate those atoms. But when we form new ones, then that's how you release energy. The reason why this feels a little bit different is that your bonds that are being broken, those are all in your reactants. The bonds that were being formed are all in your products. So it's a little bit backwards than what we had talked about before, which was the delta H of the heats of formation should always be your products minus your reactants. For bond enthalpies, it's a little bit different. And that's because we have to, the way that we are given the information is the bond enthalpies are all defined as being positive, and they're all said to be the energy required to break the bond, not the energy required when you form the bond. Right? And so that's what's throwing it off. And so if we were to think about that, which is more stable at room temperature, a CO2 molecule or two separate CLs? And what's that energy difference between them? Well, if we go back and we look at our bond, when we bond a Cl with a Cl, there's 242 kilojoules of energy holding that together. So individual atoms are always more stable by 242 kilojoules per mole. And that's because that's the bond dissociation energy, so the amount of energy required to break it apart. Or to transform a Cl2 molecule into two separate Cl1s, we have to break that Cl-Cl bond, which requires us to input energy. And so therefore, the CO2 molecule will have a lower energy and be more stable. So you're really kind of looking at CO2 to Cl plus Cl, or Cl plus Cl to Cl2. Which one is going to be a delta H that is negative? And that's because the lower your energy, the more stable you are. So if we're releasing energy because we're going down in our enthalpy, then we're becoming more stable. So if we think about this, well, that bond energy is going to be our bonds broken minus our bonds formed. And so the Cl and Cl by itself have no bonds. And the Cl2 has one bond. And so if we're looking at this, well, Cl2 to Cl plus Cl, right? So the molecule to the atoms, we're kind of breaking apart one bond. And so that is an energy of 242 kilojoules. And we're not forming any bonds. Or to go from no bonds to bonds formed, then we start off with no bonds broken, and we formed a bond, so minus 242. So for this process, our delta H is going to be negative 242. And for this process, over on this side, it's going to be a positive 242. And so we are looking for B, right? The amount of energy required to break that Cl-Cl bond means that our two atoms are not as stable as them together inside of that molecule. And so the idea behind using the bond enthalpies is that we can take all of our reactants, we can break them apart into just gaseous atoms. Right? So we can just have a bunch of those atoms all floating around by themselves, and then we can re-put them together to form other products. And so that overall energy change is going to be related to the difference in those energies of those bonds. So step one is that we have to go ahead and break the bonds to form all of our different atoms. And then step two is we're going to reform those bonds to make our products. So kind of like this. Now, this process is going to be difficult for us at this very moment. And so we probably won't do this until a little bit later into the course, because we still have to figure out how all of our molecules are connected and what bonds they're forming. And so bond enthalpies is something that we can kind of delay a little bit until we can do our Lewis structures. But we should understand the theory behind it, even though our applications won't be as useful until after we can predict our bonds inside of a molecule. Now, we talked about our enthalpy changes as being extensive. What that meant is that when we flipped our reactions, then we had to adjust the amount of enthalpy that was being released by them. And that part still holds true. Right? So when we write out something like this, the interesting part about it is that while this whole reaction has this many kilojoules, you can also think about it as being related to each of our different reactants. So this energy, 1 mole of C3H8 gives away negative 2,044 kilojoules of energy per mole when it gets combusted, right? When it gets burned with oxygen. On the same side, you need 5 moles of that O2 for that exchange. And so there's kind of a relationship between them. How much energy is being associated just with one of these, how much energy is being associated with our O2. So generally speaking, when we talk about enthalpies of reactions, we're talking about it per 1 mole of reaction, which in this case would be per 1 mole of C3H8 or 5 moles of O2 or 3 moles of CO2 or 4 moles of H2O, right? So as you're going through this, you might want to find out how much enthalpy is required to do something, like how much enthalpy is required to combust 3 moles of C3H8. And then you might have that equation. And so you would take your 3 moles of C3H8 and multiply it by, well, 1 mole is negative 2,044 kilojoules. So 3 moles should be 3 times as much. Okay, and so that's how you can also start to use the enthalpies of your reactions. Very good. If you want some more practice with this, there is the Hess's Law worksheet that's below. There is going to be a problem solving video that goes with that as well, but I would definitely recommend that you try that out. It has you write out some heats of formation reactions, and then you use the ones that are provided there to kind of figure out the missing one. All right. The last thing that we're going to talk about is latent heat. So latent heat is the amount of energy absorbed or released during a phase change. So what we've been doing so far is that all of our calorimetry occurs in one state. So it's only been in water. But we haven't been talking about, well, what happens when you take ice and you turn it into steam, right, when it goes through a phase change. So when you go through this, then between our solid to our liquid, then that's going to be our melting. Between our water to our steam, that's going to be our evaporation, right, or vaporization. Now, each of those plateaus are related to a phase change, and that's where our latent heat is. Now, the reason why they're called latent heat is it's kind of like a hidden heat, because during that process, the energy is not going towards heating or changing the temperature. The energy is going towards breaking up those forces that are holding it together as a solid in order to allow it to move as a liquid, or to break up the attractive forces that hold it as a liquid to let it become a gas. So the heating curve for something like water is in the first stage for our ice from A to B. That energy is put in just to warm that ice. And so we can do that using our MCAT type of equation. And so it would have its own specific heat capacity. For sections 2 to 3, what we need to do is, well, we need to melt that ice. Now that we've made it to 0 degrees Celsius, that's the melting point of our ice. And so all of that energy that we put in next isn't going to change the temperature. It's going to melt the ice. And so that has an enthalpy related to it. And that enthalpy is the delta H of fusion. And so this is the enthalpy that comes as you go from a solid to a liquid. Now, how you know whether it's a positive or a negative kind of depends on which way you're going, right? Now, when things are going from being a solid to a liquid, then they should be gaining enthalpy. And so we can use that to determine that part. One way to remember that your enthalpy change for a fusion, so from going from a liquid to a solid, is that it's positive, is that you can think about, well, it requires energy when we go from to break apart that solid. And so we have to put energy inside of that in order to make that happen. Whereas when we go from a liquid to a solid, that happens by removing energy, which is why our temperature is going down. And so that's going to be our negative process. Okay. So on this third section, that's going to be from C to D. That's just going to be us warming the water. And so we should be back to cube MCAT. It should have its own specific heat capacity. Section 4, well, that's us converting that water into a gas. And so that's related to the enthalpy of vaporization. And then the last part, now that it's as a gas, then that's us heating that gas. Not condense, it should be warm steam. So it can become a very involved process as you're going through these heating curves for water. And so this is why for a lot of our calorimetry, we try to stay in just one state, is that way we don't have to worry about these latent heats. But latent heats is a really useful piece of information. It's why when you add ice cubes to your drink stays cold for so long, is that before that temperature can change of your drink, it first has to melt your ice. So it has to do this whole process here for all of your ice cubes before it can do this process. So the more ice we have, then the longer it takes for that to happen. And so for our heating curve, we want to go ahead and start piecing together some different options. So a sample of ice is at negative 25 degrees Celsius, is placed into 75 grams of water initially at 85 degrees Celsius. The final temperature of the mixture is 15 degrees. What was the mass of the ice? And so we kind of have a lot going on there. So if we want to imagine that, our ice is starting off down here, negative 25. And it's moving on up. Our water is starting up here at 75. And then they're meeting somewhere down here. They're meeting down at 15. So our water doesn't have to go through any phase changes, but our ice definitely does. And so if we want to set up that type of equation, we're going to need more space. So I'm going to use that whiteboard of ours. All right, so we really have two situations. We have the heat of our ice, which is going to be the negative of the heat of our water. Now, our water is a little bit simple. Our water is just going from the higher temperature to that lower one. So we can do the MCAT, and that our mass is going to be 75 grams. Our C is 4.184 joules per grams degrees Celsius, and our delta T is going to be our final temperature, which is 15, minus our initial 85. And so we can update this in that we have 75 grams, 4.184 joules grams degrees Celsius, and our delta T, which is going to be negative 70 degrees Celsius. So that side, pretty straightforward. The other side, not so easy. So we need to do 3 things. We need to take that ice and we need to take it to 0 degrees. Then we need to take that ice and we need to melt it. And then we need to take that water now and bring that up to 15 degrees. So kind of a lot going on there. And at the same time, we don't know the mass of it. So we kind of have 3 steps going on there. So let's look at the first one. How can we take that ice and go from negative 25 degrees to 0? So our M1, we don't know the mass of the ice, but we do know that the C for our ice should be 2.077 joules grams per degree Celsius. So I'm getting that from that phase diagram that we just did, that I had just showed you with the latent heats. Now, if this was an exam or a quiz, I would provide you with that. Our delta T would be 0 degrees Celsius minus a negative 25 degrees Celsius. So a 25 degrees Celsius change. So on that first part, if we now put this into Q equals MCAT, the amount of energy needed for us to heat that ice to 0 is going to be 2.077 times 25. And so whatever our mass is times our mass of our ice, that's going to be our first part. Okay, let's add our next one. Now for our next one, we want to go ahead and take that ice and we want to melt it. So we need to put in energy in order to make that happen. And so the delta H of fusion is going to be a positive 333 joules per gram, right? Because it's taking energy for us to melt it. And so that's going to be our mass of our ice. $333. Oh, that's terrible. Times our mass of our ice too. All right. So now our last part is we need to go ahead and now we need to take our water that we're going to make with it. And we need to use our C, 4.184 joules gram degrees Celsius. And our delta T, this time we need to go from our 15 degrees. Sorry, from our 0 degrees where ice melts up to our 15 degrees. So this becomes 15 times 4.184, which is now going to be our 62.76. So kind of if we put all of those 3 steps together, even with all this, still going out of space. All right, let's erase this, make this big. All right. So I'm going to use the orange for all of our ice side. So our ice starts at 51.925 times its mass plus 333 joules per grams times its mass. So this was to heat the ice. This was to melt the ice. And then the 62.76 joules per gram. This was to heat the melted ice. All of that should be equal to the negative of our 2,196.6 joules, which is the energy lost by water. Okay, so we need to consolidate those. So we add the 333 and 51.925. So all of this becomes 447.685 joules per grams times the mass. This becomes 21,966. And so our mass becomes 49.066 grams. And then okay. Just want to double check that. A lot of math going on. Want to make sure we got that right. And so when you're trying to set up these next equations, just try to remember about where you're located on our chart. Are you starting from here? Where you're ending? And so that way you can figure out what's going on. So in this case, this was where our water initial, this was our ice initial, this is our final. So our water needed to drop down, stays in the same phase. Our ice needed to come up, transition, and then come up some more. And so that's how you can kind of figure that part out. Okay. So keep working on those. And then there are some sample problems down at the end of the worksheet to work on Hess's law. Good luck.